Today on CC Minds, you'll watch a segment about renewable energy, a contemporary and essential topic for society. This content is meant to discuss the importance of using clean energy to avoid greenhouse gas emissions, which is vital to climate change initiatives. The video briefly discusses the market, the second most important source of energy, which is wind, the machine, and the principles behind the technology.
Today, I'm your host to a journey through renewable energy and mainly wind turbines. Before I start with the topic, let's go through my background just to let you know who is talking to you guys. So my name is Jaro Martins. I am a Director of Research and Development at Dash North America. I sit in Cambridge, Ontario, Canada, and the company has 3 facilities throughout North America. I'm going to show you a little bit later. I have a PhD in mechanical engineering. I have a project management diploma by PMP. I'm trained in lean manufacturing Toyota system, which is basically designed for lean enterprise system, or Sigma. I am certified Six Sigma, and I'm a former professor for disciplines or topics like machine engineering design and quality. When it comes to industry, I have experience in mining. I designed machines and equipment for processing minerals in the past. Then I moved to auto parts and automotive industry and also race cars. And currently I'm working with energy and renewable energy at Dash North America. Up to now I have 45 scientific papers published and 145 citations globally. Today we're going to cover these aspects here, these topics. First of all, I'm going to start with the company, a brief overview about the company. What are the products of the company, where are they applied, etc. And then we're going to talk briefly about the wind market expansion. Then we go through the machine description, the wind turbine description, then the variables and a little bit of math, just to give you a physics principle of the machine. And then we're going to end up with how Dash can contribute to this market. First of all, an overview about Dash, about the company. The company was founded in 1906 by Mr. Dash, and at that time we started repairing steam engines. There were many milestones throughout the time, but I can highlight a few of them. For example, Dash Canada was founded in 1986, but from 1906 to 86 we developed special couplings, special clutches, dry, wet, and manual clutches, most of them tailor-made. And also, we start with planetary gearboxes on 1967. This is our main specialty, gearboxes, clutches, and couplings. All of them tailor-made, designed according to the need. 1999, we had Italy founded, then we had Hendrik Dash, this gentleman assuming as the CEO of the company globally. In 2010, Dash China was founded. His brother, Olaf Dash, started as part of the board of directors in 2013. Dash do Brasil, 2013. Dash USA was 2017. And then in 2018, we have Dash Dallas. In 2019, Dash in Europe and Asia were acquired by Nidec Group. So Nidec Dash is the brand, the company that is in charge of Europe and Asia. For North America, the company remains family-owned. So our CEO is Mr. Dash. For 3 facilities, we have one facility in Cambridge, Ontario, Canada, another facility in Akron, Ohio, and the third one in Dallas, Texas. So our product can be used in many applications. This is a bunch of applications that our clutches, couplings, and gearboxes are installed. For example, presses with servo drives, construction machines, recycling applications, as well as machine tools, marine, agricultural, aluminum and steel, tailor-made gearboxes, robotics, automation, cycloidal gearboxes for robots, rubber and plastics, very precise clutches, and energy gearboxes as well. This is just an overview about the products. Azimuth gearbox, very close to the yaw drive, we're going to talk a little bit later. Special clutches, servo drives, Revox, T-Vox, which is a combination of a clutch and a planetary gearbox, very special and is launching a new product by Dash, and antenna gearbox that we called Zero Backlash. Let's go now into the wind market. So we're going to talk about the Canadian market and the North American market. In Canada, so we had a very substantial growth since 2000, year 2000, when we have 114 megawatts of energy generated by wind turbine. As you can see, there was a steep growth, and in 2019, we could reach 13,000 megawatts of power, which comes to the growth that the government was expecting, that is 2.66%, and this is still projected until 2029. So this raise on the investment on wind turbine complies with the Canadian policy commitment for greenhouse reduction until 2049. This graph on the left shows the sources of energy that US has. So as you can see, you have petroleum and other sources stable. You have the nuclear power that is also stable, generating around 750 billion kilowatts hour. And then you have coal that was up here close to 2000 and then dropped significantly until 2020, and then remained stable. Differently from renewables, that you have a very steep growth. And natural gas also have a growth and then a moderate growing. Coal, as I mentioned, is very stable. When it comes to renewable fuels only, so as you can see, the geothermal is basically stable. Hydro source of energy is also stable. Solar panels or solar energy is very steep, and wind turbine or wind energy went a very good raise and then a little bit moderate, but it comes back to the growth that is expecting on this market. In terms of size of the machines, so in the 19th century, we have only from 1 to 12 kilowatts of electricity generated by wind turbines. And the machines start growing, getting taller, taller, taller. And most of the machines in the market nowadays that need service, and this is where Dash goes with providing the service, is around 2 megawatts. But the design of the machines hasn't stopped. As you can see, in 2025, we're going to have a machine that will be able to generate from 13 to 15 megawatts of power. If you compare this machine with a nuclear power plant, is a ratio of 100. Most likely, you need 100 machines, 100 wind turbines to cover one nuclear power. But let's talk a little bit about the terminology. What is this wind turbine? What are the components? How are they called? And what are their main functionalities? This is an overview of a wind turbine. I'd like to highlight a few important points. For example, the rotor blade is composed by the blades here, as you can see, and the hub. Here at this part, we call it a nacelle that has the generator, the gearbox, and the main shaft, everything. And here I'd like to highlight also that there is a sensor here that basically is one of the most important parts of the machine, because the sensor measures the intensity of the wind and the speed of the wind. Sorry, the direction of the wind. So two main points. When this sensor checks that the direction is not accordingly to the flow or laminar to the machine, so it has to turn. But I'm going to talk about it in the next slide. This wind orientation control is all the yaw drives are installed here, and every 7 minutes in average, this whole compartment with the blades and the hub, they align to the wind direction. After the energy is generated, it comes down by the cables and then it reaches the transformer station. We call it the wild voltage. After it's stabilized, it goes and is fed to the grid. But let's go now a little bit deep on the machine. So what do we have? The machine has the blades, as I mentioned before, 3 blades normally. And then there is a pitch system that basically pitches the blade according to the speed, the velocity of the wind. If it's too strong, it pitches to the neutral and then you don't have traction. The same thing is applicable when it's too slow. You cannot generate energy. It's not cost effective to generate energy if the speed of the rotor is very low and the speed of the velocity of the wind is very low. The pitch of these blades is controlled by this hydraulic system. Dash, my company, we are capable to service also this pump. This yaw drive, as you can see here, basically you have 4 to 6 yaw drives. It basically drives the main nacelle, all of this compartment, as I said before, to align with the wind. Briefly, the blades turn because of the traction from the wind, drives this main shaft to the input side of a gearbox. In terms of torque range, if we're talking about 1.6 megawatts gearbox, we are reaching 1.4 million Newton meters as the input torque, but a very slow speed, like 12 to 16 RPMs, the rotation of the blades. And then it's multiplied, the velocity is multiplied here, and then you reach around 1500 RPMs to the generator. So main points are the pump that basically drives the pitches of the blades, the gearbox that is basically a multiplier, so you have low speed, high torque in the input, and high speed, low torque in the output. This is the generator, and the electricity generated here goes down as I mentioned before. But you can ask, so why does a wind turbine have 3 blades? So it's based on this graph here. What do we have here? On the axis here we have the lambda, which is basically an equation that multiplies the angular speed of the rotor times the radius of the blade or the machine and the velocity or the wind velocity of the air blowing into the machine. On this y-axis, we have the efficiency of the machine. It means that not all the wind that is blowing is harvested and transformed to electricity. You have partially this energy transformed from kinetic energy through electricity. As you can see, different designs, but the design of the blade that gives the highest efficiency is with 3 blades. And this lambda ratio should be close to 7. So this is the initial state that the engineer takes, the initial information the engineer takes to start designing a machine. And this efficiency is basically was determined by Betts, it's called Betts index, CP, and is the division between the ratio between the energy produced by the wind turbine divided by the total energy that the wind has in it. But let's talk about energy now. So we are talking about transforming kinetic energy in electricity. How does it work? So as you can see in this sketch, you have the wind blowing here, the wind turbine, and then you have a VI. The VI that is coming in is smaller than VF that is higher than the VF that is coming out. So you have a higher speed here and a slow speed here. Why? Because you are harvesting part of the energy, kinetic energy of the wind, and the remaining energy that you could not harvest goes away. And this is the equation that we learn at school, high school, or college, whatever, which is kinetic energy is half of the mass times the velocity squared. As you can see, the velocity of the wind is very important because it's power 2. And the mass of the air is also important. But if I start playing with this equation, for example, the mass of an element can be calculated by the density of this element. We are talking about the air, the density of the element times the volume, right? But you can ask, does the density changes? Yes, absolutely. When you have low temperature, the density of the air is higher than when you have warm temperature, which is lower. To give you one example, when you have the warm temperature, the density of the air is around 1 kilo per cubic meter. When it's low temperature, 1.2 kilos per cubic meter. This is kinetic energy, right? So, but now I can play with the volume. What is the volume? The volume of the air is the area of this rotor here, which is this diameter here, times the distance. We can assume a distance L here, a unit of distance L that is coming in the blades. But now I can tell you, oh, L is distance, right? So it's the distance of this column of air. If I divide the L by the time, I have to divide the kinetic energy by the time. The time most likely is in seconds. So if I divide a distance by time, I have velocity again. And if I divide the kinetic energy by time, I have power. So now I'm getting close to the final equation that helps me to design a machine. So the power is half of the density of the air times the area that is the frontal area of the wind turbine times the velocity that was from the last L divided by S times velocity squared. But this velocity here is multiplying, as you can see, velocity times velocity squared. I have velocity power 3. So, and then I am pretty close to the final equation. The only one index that I have to add is how much is the efficiency of the machine, which is the CP that I just mentioned before. Just remembering that upstream velocity is oncoming wind velocity and unused wind energy is in the downstream of after the blades. So we went through the whole play with the equations. We start with the kinetic energy, basic equations, and then we replace the mass by the density times the volume, and then we add the area times a unit of distance. Then we divide both by time. We reach the power. The power was half of the whole area times L divided by T, which became velocity, and then multiplying both velocity power 3, and this is the final equation. This is used quite significantly when you are going to design a gearbox, a wind turbine, but mainly when you operate it, because the power is very sensitive to the velocity. You have to take advantage of the energy available in the wind, which means that the yaw drive, the main drive, mainly the yaw drive, has to look for the best stream to harvest as much energy as possible. How does a dash plays in the market? So we basically redesign the main drive or the gearbox. And to give you a perspective how it works, as I mentioned before at the beginning, we have an input, torques on the range of higher than 1 million Newton meters. You have a planetary stage. The torque goes to this direction, to the intermediate shaft, and then to the high-speed shaft, and is connected to the generator. How to design a gearbox, how to reverse engineer a gearbox, how to service a gearbox, analyzing all the forces, all the stresses on the main components, analyzing the flow of the stress, as I mentioned before, that comes in the input side to the planet carrier, to the low-speed shaft, intermediate shaft, and then goes to the high shaft and end up on the generator. Another very important strategy is to analyze all the failures in the field. So we, at Dash, we analyze all the gearboxes, multi-brands in the market to check their main points of improvement, I would say, areas of improvement. And this is what we do. We service the gearbox and we improve them. This is the yaw drive I mentioned that basically changes the position of the nacelle. So we design, so this is a cross-section of the yaw drive, and this is how we work. We also analyze the microstructure of the material used for the casting. We run all the numerical simulations to verify the weakest points and make them better. And also we evaluate the stresses and the fracture when the parts are broken or they come from the field. In summary, what we saw up to now, we saw that wind turbine is the second main source of renewable energy. This is by far important. The market in Canada and US, both are growing. In Canada, 2.66%. In US, as you could see, there was a high demand of this source of energy. In terms of mechanical energy, so this I missed a little bit, but you guys, engineers, you know that mechanical energy is potential energy and kinetic energy. We basically focused on kinetic energy, which is the energy of the movement. When you talk about energy of an object, if it's moving, you are talking about kinetic energy. If you have an object falling, you have a potential energy, or if you have a spring compressed, you have a potential energy. But in our case, in the wind turbine, we talk basically about kinetic energy. Another very important statement is kinetic energy is harvested from the wind, as I mentioned, partially, not fully. Wind has an intensity, which is measured in meters per second, and a vectorial direction. There is a vector, so you have to look for the direction of the wind to take as much energy from it and transform to electricity. Kinetic energy is harvested partially. Betz coefficient shows the possible amount of energy harvested from the wind. And this Betz coefficient is very important because you can see the different designs of the machines, and you can have a very good idea the reason you have most of the 100% of the wind turbines having 3 blades. And the main components of the gearbox are, as I mentioned before, the gearbox, which work as a multiplier, and the yaw drive to turn the nacelle, and the sensor that is measuring constantly the velocity and the direction of the wind. So we end up showing a little bit of the main drive and the yaw drive, and how we from Dash can improve the product by applying a service on multi-brand gearboxes. And with all of this information, I end up my presentation. If anyone wants to contact me or wants to have more information about green energy, renewable energy or wind turbine, at the bottom right you can see my email. Feel free to contact me. Thank you very much for your time and have a wonderful day.